Stefan from Utrecht University. And to start by presentation by Mr. Lever.
Thank you very much. Should I speak for a period of time and take a break, or does this session just run for?
After an hour, 1 hour, maybe.
Take a brief break.
5 minutes.
Okay, I see. All right. Well, thank you very much. I really appreciate the opportunity to come here, and Professor Mohandas for inviting me. I've known many students from Iran at the University of Illinois for many years, and they've been very smart and very friendly, and they've always said that I should visit their homeland, and with great enthusiasm. And so I'm happy that I finally got a chance to come. I've had a good time so far. I visited Shiraz and Isfahan the last few days, and now I'm spending time in Tehran. Let me give a little bit of introduction for a few slides, and then I will get into the main part of the this short course or tutorial. As I said, I want to thank my host and the funding agencies that sponsored this. Here's the overview of the topics I will give after this introduction. There are 4 main parts, I would say. One is sensing, one is filtering, one is planning with perfect sensing, and then one is planning in information spaces. And then there's some conclusion kinds of things and possible futures. As most of you, I think, know, there's already a tutorial paper that I've provided that is available on the webpage here, and it's also going to appear soon in a series of monographs called Foundations and Trends in Robotics. I think that will appear in October or November, but you can have it now. So they're early. And that corresponds fairly closely to my presentation. So if you have trouble understanding some things, it's maybe helpful to read over some of that. All right. So how did I get into this tutorial? Well, one of the things is I've worked in planning for many years. I guess it's coming around on almost 20 years or so, working on planning. And in 2006, I finished it in 2005. In 2006, I wrote a book on planning algorithms. And one of the things that sort of bothered me about the planning research and the algorithms and the techniques that people were using is that sensing often comes as an afterthought. Like in robotics, which is my main field, robots see the world through sensors, right? They start off basically blind. They don't get information the same way as traditional computers, I would say, right? So just imagine that all of the information that gets into the robot, you can get some initial information, maybe a priori, but almost all of the information that the robot gets comes from sensors. So, but previously in planning, it seemed like the information just kind of comes for free, and then the algorithms begin to do their work, right? And I felt uncomfortable about that. So we tend to plan these perfect kinds of things called configuration spaces. I believe you had some overview of that in the last couple of days, if I'm not mistaken. And another thing I should say, by the way, is this book, you can download it for free also if you're interested. It's not the main topic of this course, because this course is what I've been interested in more recent years. So I'm giving you kind of an update of where I went after the book. But you're welcome to download that if you like. Interestingly enough, there's getting close to 1 million downloads of the book. And if I look at the top 4 countries, it's US, China, India, and Iran. So the 4th largest country in terms of downloading this book that I wrote is all of you. So it's very nice. Why is that happening? I think one, which I always hear from my students, is that robotics is very popular in Iran, and that makes me very happy because some people like robotics, some don't, but it's great to be in a place and feel very welcome for this topic. The other reason probably is that there's a strong mathematics and science tradition here in education, and I think the combination of those two fit together well with my book. So anyway, so that's also another motivating reason for coming here. I feel like I should have a lot of robotics friends, so that's very good. So what I was saying before about perfect information that kind of helped motivate this tutorial is that we imagine that we give exact geometric models to the computer. This is a classic way of looking at planning, sometimes called the piano movers problem. You have an exact geometric description of the piano, and instead of humans here, I just got some funny picture of robots trying to manipulate a piano. But imagine you gave all of this model to the computer. It's all as if it were generated by a computer-aided design CAD system or something, and then you begin to do planning, right? But this is already a lot. How do you get all of this information? Do you hire graduate students to measure everything? Do you get very expensive sensors, laser scanners, and try to map everything out? People can do that. But in any of those cases, you never end up with models as perfect and beautiful as this. And in fact, most of the applications of planning, even though it came out of robotics, most of the successful applications are outside of robotics. In areas like virtual prototyping, in, say, video games and virtual environments where you actually have geometric models like this, almost for free. So that's kind of interesting, right? So it sort of suggests that even though maybe the robotics people have been good at coming up with interesting problems that are general, it might not, what they were trying to come up with to solve a basic problem for robotics might not be actually fundamental to robotics, or let's say most applicable to robotics, because it makes some unreasonable assumptions about the model. Now, having said that, these algorithms have been quite useful in robotics as well, but it's interesting that I think the most compelling uses, going all the way to industry, have to do with problems for which the world is virtual, let's say. Because that's the way that the problem is formulated. It looks like this. And as I said, I think you had some overview on configuration space obstacles. I just want to point out a couple of different spaces here that will come up. One of them is the configuration space, which is the space of all transformations that we can apply to a robot. So, for example, if the robot can only translate, then if there's a rectangular obstacle in the robot's environment, then the set of all translations that I can apply to the robot looks like this. Set of all translations that I can apply to the robot in which it hits the rectangular obstacle, right? So that would correspond to this thing called C-ops here. And what happens in general is that we have some high dimensional, maybe high meaning 3, 4, 10, 100, or 1,000 dimensional. A humanoid may have 80 degrees of freedom, for example. So for every degree of freedom, we have a dimension in this configuration space. And then the pathfinding problem, the way we abstractly view it, is that we want to go from one place to another, automatically computing this kind of path. And then these places where we are not supposed to be because of collisions are very hard to directly represent. We can do sampling of these regions to figure out if we're inside or outside of them using collision detection algorithms and so forth. But I just want to point out that the configuration space idea was fundamental in making progress towards motion planning. And that idea actually goes back to Lagrangian mechanics. So if you have some background in mechanics, you may have seen configuration spaces there. They form the basis of differential geometry and the reason why people are studying manifolds and all of these kinds of things. So, it was the right idea. It doesn't depend on what shaped robot you have, right? If it's a humanoid or an autonomous vehicle, a flying aircraft, all kinds of different robots you can imagine, they all look like this. You're trying to get from one place to another in a configuration space. So I would argue that finding the right space in which the problem lives, let's say, is critical to making progress. And it was in the case of motion planning. So I've been interested in this thing called an information space recently. And, well, at least for the last 10 years, but after finishing my book, I went really into this a lot. And most of my funding over the last few years has been involved in heading some very large projects that involve trying to study the foundations of sensing and developing these information space ideas. So what I've been interested in is formulating these things called information spaces, formulating sensor models, and doing computations over these information spaces. And maybe eventually we'll have things that are sampling based or combinatorial forms of planning over these spaces, which may parallel in some ways the things that we had in motion planning or path planning. So I feel like, for configuration spaces, the early steps were already done, but we have to develop these kinds of things for information spaces. We don't have, Lagrangian mechanics doesn't just already have the structure that we need, that we just kind of borrowed in robotics to make our configuration spaces. We have to really find these spaces and characterize them. So, the idea of information space, if you're curious, I think the oldest reference I could find is a famous book by von Neumann and Morgenstern, which back to 1944, which is considered one of the classic books, maybe the classic book on game theory. So maybe you've heard of that book before. Another reference by Harold Kuhn. The idea of an information state is, in a decision theoretic context, what information do you have to make a decision? Right? So what information is available to make the decision? So in general, this kind of idea comes up in sequential decision making, and sometimes sequential decision making is called extensive form games in game theory. It's also been quite useful in stochastic control theory. So control theorists, because control theory is also nothing more than sequential decision theory. Right? Sometimes the sequence is taken to the limit, so that it's a continuum of decisions, but nevertheless, it's sequential decision theory. And it comes up in robotics somewhat. Certainly in artificial intelligence research, you see things like belief states, maybe knowledge states, things like that, also reflect this idea. What information or knowledge do you have at the point at which you make the decision? So it's very interesting to characterize these spaces and try to simplify them as much as possible. And sort of imagine that the classical state, say of a machine, you imagine how it might look. You write down the information on the Turing tape, and then the machine starts to compute. Versus something that's kind of sensor-centric, where the machine M interacts with the environment E, and you can sense, the machine can sense the environment. The environment's a physical world here. And then actuation can control it. So in some sense, that interaction is quite a bit more complex, I would say, than the interaction of moving a head back and forth on the Turing table, let's say, right? So this whole thing was beautifully designed to, in some sense, allow you to ignore the physical world, right? That's the beauty of computation, in that you've abstracted the physical world away using logic, and everything works in a beautiful, clean, predictable way, which is wonderful, right? I mean, that's the great power of computation. But for robotics, it's not so accurate to view it that way, because you're always dealing with this physical world E, let's say, and because of that, it suggests making different kinds of models. And we still want to do computation at the end of the day, let's say. So this is a course about computation. But I just want to argue that we should consider together internal computational state and external state of the physical world and analyze the whole thing together in some way. And that's going to be the kind of the way of thinking about this. And then we study the measurements that come from the physical world and then talk about how to do computation with it. Some possible surprises. Some people have expectations about what I might cover in this topic. A lot of people make a big deal out of discrete versus continuous models, and especially led to hybrid systems and control theory and other areas. Not very important in this tutorial. So some of the things I talk about will have discrete or continuous versions, and it doesn't really matter that much. A lot of subjects people say, oh, like for example, computer scientists like discrete things and electrical engineers like continuous things. I don't care. It's not going to make that much difference here. And so it's not going to be a significant distinction in the things I talk about. Another thing is talking about information spaces, not information theory. So sometimes I can talk to somebody for half an hour and keep insisting that I'm not talking about information theory, and then they still will come and say, yeah, but isn't that information theory? And no, it's different. So you've maybe heard the subject information theory. That's due to Claude Shannon. Beautiful line of work. It's at least as old as information spaces, but people tend not to know the term information spaces as much. Information spaces are about the information you have in order to make decisions. Information theory is about communications across a channel, right? You talk about channel capacity, entropy, all these kind of things come out. You transmit messages, you receive messages, and it's generalized all sorts of things, but it's still a very different mentality from information spaces, which are more for decision theoretic or control kinds of problems, which to me are very natural in robotics. So I just want to point that out in case you're wondering about the connection. Another strange thing is I'm going to give you a lot of sensing models, and the majority of them are going to look perfect in the sense that if I knew the state of the physical world, then I can predict what the sensor is going to do. And I just want to point out, most of my colleagues will say, oh, so your sensors are so perfect, you must have perfect information. But I want to point out that perfectly accurate and reliable sensors, even the models that I give here, are going to have huge amounts of uncertainty. So I think many people tend to think that uncertainty happens only because of noise or disturbances in the outputs of the sensors. Like, oh, there's a Gaussian noise model, and that's why I have uncertainty. Well, there's a bigger source of uncertainty, which I think is often neglected, and I want to emphasize that very much in this tutorial, which is that we want to talk about simple sensors that cannot measure everything in the world. So that's where uncertainty comes from, and that they're not measuring everything. I'm not going to measure exactly where every person is in this room, right? Exactly their weight and physical characteristics and where they are sitting and their identity. I'm not going to measure all of that with the kind of sensors we're talking about. They're going to be very simple sensors. So uncertainty comes about because of ambiguity. Right? So that's different than noise, and they're independent. And I'm not against noise models. I'm just saying that there's two different kinds of uncertainty. And I hope that becomes clear during the tutorial. I thought I had 3 surprises. Okay, I thought I had a 4th surprise, but much to my surprise, I don't. So that's okay. Let's see. And some coming themes, and this is the last of my overview part. I want to start from the task. All right, a very particular task. I know one task that's popular here is pursuit evasion, right? Playing hide and seek. So all of you like the game of hide and seek, right? We play that in America too. Everyone plays that around the world, right? So you start off as kids playing it, and then I'm a parent, so I like to play that by chasing my boys around too. And everyone likes that game. So suppose that's the task. Well, what I want to do is start from the task and then understand, and I emphasize understand. I like understanding things. So I want to understand what information is actually required to be measured from the physical world, right? If you want to solve the task again. Don't try to measure everything. Think about the task and figure out what you really need to measure. You may know in some of the, as I'll mention in a bit, some of the visibility-based pursuit evasion work, is some of the fine work from this group here, that you don't have to measure the position of the evader, right, to solve those kinds of problems. I feel like that's just the beginning, right? How much more can you do without measuring everything? I think people were surprised in when the early visibility-based pursuit evasion work came, because they thought, wait a minute, don't you have to describe exactly what the evader is going to do, and don't you have to estimate where the evader is going to move, and don't you have to put probability models everywhere on top of it? No. It works very cleanly and nicely just by imagining the evader is moving like a gas, right, filling the space and such. And it's a kind of simplification that involves leaving it ambiguous, right? Don't specify it. So that has to do with starting from the task, I think, and understanding. So I'm going to go more and more in that direction. I'm going to introduce something called combinatorial filters eventually. I hope that's appealing to computational geometers. I think I put the word combinatorial here because I learned from studying computational geometry that combinatorial reasoning is the kind of fundamental ideas of how to, let's say, exactly discretize geometric problems. And I feel like there's a beautiful class of filters we can design that are much like Kalman filters and Bayesian filters, things you see a lot in robotics, but have these kind of beautiful combinatorial principles built into them in some ways. And I hope to give you that kind of feeling. So, in other words, it's like what would sensing models and filtering models look like if you applied a kind of computational geometry philosophy to it. I feel like it's that way. Maybe I've not done a faithful job of fully thinking like a computational geometer, but it definitely inspired my way of thinking for these kinds of things. The longer bullet here, this says that we may have some enormous spaces that we define. So much, much bigger than configuration spaces. That sometimes worries people because they're accustomed to estimation. They feel like I have to figure out where I'm at in that space, I have to characterize that space, I have to compute over that space. I'm going to define large spaces because then I want to do analysis over that space. And I will say that large portions of that space can remain ambiguous, and that's going to be good for us. So in order to make that kind of analysis, I have to define a big space and then show you that I don't have to measure everything in it. So that's why there's going to be some big spaces, and usually, if you're, suppose you work on graph methods or network problems, algorithms on graphs and such. You know that if your graph's enormous, that you're going to have more and more trouble, right? So the size of the graph matters. Here I'm going to define some large structures, but they're implicitly defined, right? I could say, consider the set of all functions from the real numbers to the real numbers, right? That's an enormous collection, but it did not take me very long to describe it, right? So the big spaces we make will be like that. They'll be simple to describe, but enormous if you were to somehow enumerate or compute or do representation of it. So we're going to avoid doing that wherever possible. And we're going to try to avoid even recovering a particular state in these big state spaces. And I'm going to provide some kind of idea of something called virtual sensor models. One example of that is something you may already know well, which is the visibility sensor. Right? Just omnidirectional visibility. I look in all directions. I would call that a virtual sensor model, which could be implemented by many alternative physical sensing systems. Right? So I'm going to try to separate very clearly between real sensors and virtual sensors, which I'll say are characterizing the information that some kind of sensor should be able to provide. Right? So the virtual sensor models will live in, let's say, a mathematical world of modeling. And I want to distinguish that from physical sensors because I think when we start comparing sensors, it's easy to get confused, and it's good to have just very clear kind of models of what the sensors are on the mathematical side. All right. Are there any questions so far? That's just a brief introduction and motivation, and then I will go to the first main part of the tutorial. Okay? Perfectly clear, right? Well, there's still no details yet, right? So this is just a high-level overview, so that's quite okay. All right. Did I get the month and the year right here? Yeah. All right, good. I tried to look that up carefully there. I noticed when I got my visa to come here, it said that the year was 1390, and I thought, oh, that's interesting. So I looked it up. I know Nowruz is coming soon, right? So I'm sorry I can't stay for that. That would be fun. All right, slide 2, yep, the next one here. I want to talk about just sensing. This will be both physical sensors and virtual sensors. Like I said, if you have any questions while I present things, I think there's enough extra time that I've budgeted into these slides and such so that I can happily explain things on the board. I can clarify anything. Don't worry, if you're afraid to ask in English, I'm sure you can ask in Farsi and someone will kindly translate, right? So there should be no problem. Just feel free to jump in and ask. I want this to be an interactive class if it's possible, right? So don't worry about things like that. It's kind of a large class, and maybe it's intimidating, but don't worry. Just please feel free to ask things as we go. All right, on wonderful February 29th, which comes around once every 4 years, here we go. So I'm going to talk about physical sensors first. As I said, I want to start with physical sensors, work my way towards mathematical models of sensors, then towards filters, and then finally get to planning, right? So this would be like the prequel to planning. You heard of sequels and prequels, you make a nice movie, it's successful, and then maybe you have a sequel, which is the next one, right? This is like the prequel. I feel like this is the stuff that in some sense should have come before planning. This is like, so where do you start? I feel like you should start with the sensors and go all the way up from there. So that's how we're going to do things. I want to build everything up so that hopefully by the end of the course, you can see many different ways to formulate models that are alternatives to visibility-based pursuit evasion. There may be many different kinds of interesting models you can formulate, and I think they'll lead to very interesting computational geometry types of questions and such. And they'll be also very strongly inspired by real robotics questions, which I think is very nice. So that's what I've been trying to do. Well, here's the first problem we have when we think about the physical world. Imagine we're in the physical world, I'm talking about physical sensors. What is a sensor? I read a bunch of books on sensors, physical sensors, and what do you call it, handbooks on sensing and these kinds of things. And it's interesting to see the introduction where they try to define what a sensor actually is. Most often I see that a sensor is supposed to be a transducer. Has anyone heard of a transducer? Transducer is a physical device that converts one energy form to another, and a sensor should be a special one that converts some energy form into an electrical signal. Right? Fine. I have a hard time imagining the GPS on my telephone, let's say, as being a sensor as simple as that. So it's doing all kinds of things involving satellites in space and everything else, right? So it's hard to know. So, maybe this light-dependent resistor, right? A resistor that changes its resistance based on light, photoresistor, maybe that's a good example of a sensor when I put it in a circuit. It can change the voltage or current based on light. So it's converting light into electrical signal changes, so that's very nice. But by the time I get to GPS, I have to say, well, that's quite a bit more complicated, right? There's an entire computer inside. That's an older picture, I guess. Now our GPS units are so small, they're just everywhere. So it's not so simple. There's also the problem that maybe I did not even design the device as a sensor, but it gets used as a sensor later. Like a lot of people have just borrowed wireless cards, right? So I have a Wi-Fi card, and maybe I can just look at the intensities of the different Wi-Fi signals that it receives, and I can determine what room I'm in, right? Right? I think when we were sitting in Professor Mohavis's office, there's a different collection of Wi-Fi sources than here, right? If I stick that on a robot, it's going to learn something about where it's at based on that information. So I could abuse this device and call it a sensor, but normally people don't design it that way. So it's kind of interesting. Another weird problem is this is the American-style toilet here, let's say, but there's this mechanism here that floats in the water, and it moves up and switches off the water when the toilet bowl is full. Right? It does this automatically. So is there a sensor in there or not? A lot of people look at it and say, oh yeah, sure. But if I go back to the definition that people give in the sensing books, that a sensor is a transducer that converts energy into electrical signals, where are the electrical signals in here? So I guess that is a hydraulic circuit, right? It's like a water-based circuit. And I guess there's a sensor in there, but really, I have a feeling that the idea of a sensor is quite elusive. Like it's just something that we impose on it. We see a device and we imagine there's a sensor in there, and we can kind of try to define it. Yeah, it must be this thing with a switch in there somewhere that's turning off the water. You say, oh, that's a sensor. But I really think it just corresponds to our our intuition, our superimposed idea about what a sensor should look like, so that if you're trying to come up with a rigorous idea of what it is, it gets quite difficult, right? So I don't think it's as simple as, it's not as clear as defining what an algorithm is or something, let's say, right? We have pretty good definitions of that, going back to say, Turing machines and such. But I just want to say that, in the real world, I'm not even sure what a sensor is. It depends on how you use it. It depends on the type of circuit, I suppose. And I just want to make that clear. I don't have a satisfying definition of a sensor. But I'm then going to go to mathematical models, and then we can just define whatever we like, right? But I want to hope that they correspond to the way that people use sensors in the physical world. I'm going to give some examples of different kinds of sensors in a bit, but I just want to point out that we don't have a good idea of, clear agreement on what even is a sensor sometimes in the physical world. All right, I'm imagining different kinds of problems. Here's some example scenarios where people are using sensors that maybe kind of inspire some of the things I want to talk about. Perhaps you're in a shopping mall and you want to keep track of how people are moving, maybe with cameras and such. Could be for security, but most often people want to track, the owners of the mall want to track how people are moving so that they can determine where to place the advertisements, right? To make more profits, right? To make sure that when they're shopping, they come by the right displays and such, right? I see the approach here for the workshop was to put advertisements everywhere, which is wonderful. So I feel very special, and that's one solution. I think here they have to compete, right? So they want to figure out where are the critical places so they can charge more money in. This is very interesting. Imagine a control room like this. Imagine you have a bunch of cameras and you're watching a building, and maybe you see a person go through one of the cameras, and then you see them go through another screen, and then another screen. What can you infer about where the person went? Or better yet, what can you infer about the structure of the building? Right? Just by the fact that they went from one camera to another camera to another camera, and if I don't know anything about the structure of the building, maybe I can learn something interesting about how the building is arranged. Right? Because there may be certain ways, it may be impossible to go from one place to another without going through one camera, right? And so it is revealing something about the structure of the environment, even if you're sitting in a control room. I find that really interesting, right? Somehow all of these issues are coupled together in a very interesting way. Assisted living is a good example. There's a lot of interest in that, in robotics and sensing, taking care of the elderly. So imagine you put a few very simple sensors in here, and instead of a robot, maybe it's the human that moves around. And you would like to keep track of what rooms they're in and how long, things like that, so that if their behavior changes in some unusual way, then what you would like to do is maybe alert a medical authority or something, right? Like maybe the person falls down, they have not been in the bathroom for 2 days, something like that. You can find out that maybe some help is needed, right? So that's a kind of a nice idea with very simple sensors and such. And you can monitor wildlife in many ways, maybe monitoring fish under the sea or animal, wildlife, birds, all sorts of things you can imagine with sensors and such. So all these problems involve some kind of moving entities that don't really move very predictably with respect to our design of sensors and such. And we want to gather information about that. So that inspires some of the kinds of things I'm talking about. These are all examples where there's no sensors that are moving. This looks like stationary cameras. The stuff we're trying to observe is what moves. We could also put them on robots. Has anyone heard of the Roomba? So a couple of people. This is a popular vacuum cleaner robot that was built in the U.S. It was a company started by Rodney Brooks of MIT, and it sold millions, and it inspired lots of competitors. I'm sure there's Chinese versions of this now, and lots of things like that. And people also use it for cutting grass out in the field, versions of this. It mostly just runs around without much, it does not have a map of the environment. It just kind of explores in some zigzagging kind of way, trying to suck up the dirt, and uses very simple sensors. I like that. I like the simplicity of that. There's also more complicated systems. This was a famous autonomous car that won the, in the US we had this, I don't know if you heard of the DARPA challenge, but we had these challenges to build autonomous vehicles. And whoever the winner was, whether they came from industry or universities, for the first 2 challenges they could win $1 million. And then for the second challenge, I believe it was $2 million. So Carnegie Mellon won the most recent one of those, which was driving in an urban setting. There's even a better one than this. If you're curious, you could Google for this. You may want to look for the just look for the Google car. Google has developed a car. The same guys who did this went to Google, and then they developed a system that drove all by itself, a car that drives by itself, 200,000 kilometers they've already gone in the San Francisco Bay Area, which is a very crowded metropolitan area. And it works, you know, I mean, it was amazing. So autonomous driving has made a lot of progress. I just want to point out that there are sensors everywhere on these kind of systems. You can see them around us a little bit. So that's another example. Aerial vehicles. So there's all kinds of sensing there. Even in problems like protein folding, you can imagine that there's some kind of state here, and it's very hard to measure. Maybe you use X-ray crystallography as your sensor, and it provides some information about distributions of distances and such between atoms and things like this, but I feel like when you shrink everything down to a very small scale, the sensing issues really dominate to a large extent. You know, we can't, this is not the way a molecule looks, this is a model that somebody made, and so it's very hard to reason about the state and such. So even stuff like this might be a place where we might ultimately think about these sensing issues. All right, this I got from the CRC handbook on sensors. So it's a very big book. It's like about, it's about this thick, some gigantic book of sensors, which I think is worth looking at. It's fun to imagine all the different kinds of sensors that people have. It's amazing the kinds that they have. For example, you can put a couple of plates on the wall and just measure changes in capacitance in the air, and it will detect people going by and such. I didn't know that. All kinds of interesting things like that. It's very helpful to know because even if you're a theoretician and you like to do mathematical things, it's interesting to know what the real things look like so that you can invent reasonable mathematical models, I think. You know? So it's very nice. This is from this book. They divided up the kinds of things you can measure into several categories, which I found kind of interesting. For example, you can have spatial, which is going to be the most important for us. Displacement, how far did something move? Velocity, how fast is it going? Acceleration, the derivative of velocity. Distance to something, how far is it to the wall, right? Proximity, am I close or not? Position, maybe I know the x, y coordinates of exactly where I'm at, maybe I don't, right? So that's something I can measure. Altitude, what's the altitude of Tehran? Anybody know?
1.1 meters.
Really? Oh, pretty good. Okay, so it's quite a ways up. Yeah, I see. I see some mountains around, so yeah, it gets high pretty fast. Yeah, very good. So altitude, area, volume, maybe tilt, like how are we close to level or not? That's maybe useful in airplanes, I would guess. Motion detection, detecting when something moved. So another category is temporal. So perhaps I like to separate between a clock and a chronometer. A chronometer measures how much time has elapsed. It's like a time odometer, if you want. And a clock will tell like some exact coordinates, right? Electromagnetic is interesting. So there's fields, and that motivates some of the models I will give, which are field-based sensors. So within the open space that we move around in, somehow we can magically get information, right? I guess our cell phones would not work without stuff like that, right? So clearly we can sense just information out in the open. Mechanical properties. This is interesting, right? People are doing design experiments and sensors to measure mass and weight and density, force, strain, torque, all these kinds of things. Fluid properties like viscosity, temperature is a good one, right? So these are all things we can imagine measuring and using perhaps. And then after these categories, they have this kind of other category, which I thought was interesting. Chemical, radiation, biomedical, so some extras, but probably the four most interesting ones for us are up there on the top. So I just think it's helpful to know. I highly recommend, if you're interested in sensing, to go look at a handbook on sensing and flip through, and it's very interesting to see. I mean, there's hundreds of kinds of sensors that really amaze me. All right, so here's some kind of sensors that will inspire some of the stuff coming later. Very simple in robotics, a contact sensor. It goes click whenever you touch the wall, for example. Like if you push on this, it's like a button, right? So that's called a contact sensor, just a switch. Very old sensor called a sonar, right? So when they're sonars, it's like a speaker and a microphone together, right? It just blasts a sound, and when it bounces off of the wall, it can listen to the time of flight. It can calculate the time of flight, and from that, estimate based on the speed of sound, or whatever, in this case, the speed of sound, ultrasound. It estimates the distance to the wall. Has a lot of troubles because these signals tended to bounce off of walls and such. People don't like to use sonars too much anymore. That's mostly what we had to suffer through maybe 20 years ago, until different kinds of laser scanners and other kinds of technology. Do you know the Kinect? The Kinect, yeah, which is used for the Xbox. So that's really changed a lot. So the kind of sensors we have are amazing. Compass, you can buy very cheap compasses. There's one that maybe costs about $8 US or something. Provides very coarse quantized information. Compasses are frustrating because they're always subject to interference in buildings and such. You know, we have wires everywhere, and I think they cause a lot of, I think the electrical circuitry inside of buildings causes a lot of trouble. But outside, maybe it's useful. Microphone itself can be considered as a sensor, fine. In fact, the sonar is a little bit like a microphone and speaker together. Wheel encoders. So there's a common way to, in robotics, if a wheel is rotating, people will, inside the motor, you can make a wheel that rotates as well, that follows along with the actual wheel that's rolling on the floor. Or this will also work inside of a joint on a robot, anything else. Imagine there's a bunch of holes in the edge of the wheel, and then you shine a light, like an LED, and you shine it onto a detector, and then you count how many pulses you have. Right? And that will tell you how much the wheel has rolled or how much the motor has turned. Even if it's slipping on the ground, you at least know how much the wheel has rolled. So that's interesting. Stopwatch timer, that's time measurements. Occupancy detector, people use these to detect motion. Safety beam, so maybe I just have a beam that goes from one wall to another, and if you step past it, it gets detected. Very, very simple kind of sensor. Cameras. The Wii remote for the Wii game system. I think like I said, the fancier one these days is the three-dimensional, the depth information, and that you get in color from the Kinect. Right, it's quite amazing. I always like these. We have these. Still have this one near my house. It's an older type pressure mat. You step on this and the door opens. Right. I don't know if you've seen those around, but it's very reliable. It works much better than these cameras they put in modern stores that. The doors are always opening at the wrong time, and so, but this was very nice. I like pressure mats. This laser scanner revolutionized robotics in the 90s at some point, and it was the greatest thing until the Kinect, I guess. So the Kinect is much cheaper. This was about $8,000 and provided very accurate depth measurement. The kind of visibility models you might use for pursuit evasion, let's say, would correspond to a couple of these, which is typically about $15,000 worth of sensing, or something, because it's like very exact measurements and very long range and very dense and very rapid. Or visibility models could correspond to cameras if you have good software, so that's another lower cost possibility. So these are just some different sensor examples, and I'm very interested in cheaper sensors like these kind, let's say. And this tutorial is going to be much more towards minimalism, trying to make the simplest kinds of sensors and analyze those and what they can actually achieve. Let's see. So one last thing I'll say, and this comes from the sensor handbooks. We tend to find these terms. I'm not going to use these terms very much, but I want to remind you of them a little later when I make the mathematical models. The point of this beginning part here is just to, things are going to get more abstract as we go, but I just want you to be convinced, hopefully, that we're presenting something that does correspond to the real world, that these are fairly faithful kinds of models of things that happen in reality. So these are just some properties, and some of the stuff I'll define later will remind you of these, I think. So people talk about a transfer function in sensing. Usually they go from real numbers to real numbers. I'm going to make functions that map quite differently. I'm going to replace the reals and reals, but nevertheless, all over in the books, you see that there's transfer functions. And they often say that the sensor is absolute versus relative. Like, for example, some temperature sensors can tell you exactly the temperature. They will say it's 14 degrees centigrade. Some can only measure a change. They will just say, well, it is now 3 degrees warmer than it was before in centigrade. That's all they can tell you. So it's very interesting. You can fix those by a process called calibration, by the way, which eliminates these kinds of things. It gives you more information. In fact, I think a wristwatch is like that, right? A wristwatch can only tell you how much time has elapsed, but we pretend it tells you the exact time by calibration. Right? So it really is a relative sensor, but we pretend it's absolute by always adjusting it and fixing it whenever we need to. People in the sensor books, they tend to worry a lot about whether or not G is linear or nonlinear. I don't really care about that too much here. I'm going to make much crazier functions than G in a little while later. But I just want to point that out. That does show up in a lot of these books. What's interesting is they talk about resolution, which is the set of possible. So for some G of x, what's the set of possible values that I can get, right? for g of x, what are the set of possible values? In other words, that's the image of that function. So what are the different possible readings? Just like the resolution of an image, I guess, in some sense. There's also this interesting idea, which is going to be very important later. I won't use this term, but I'll remind you of it a little bit, which is sensitivity. This is starting to get at something I really find interesting, this kind of ambiguity. In other words, if a sensor is measuring some stimuli, then the sensitivity is the set of stimuli that produce the same reading. Right? So what's the set of all things that are happening in the world, in the physical world, that produce the same sensor reading? That characterizes how much ambiguity there is, or lack of ambiguity, in the sensor. Repeatability is interesting as well. I won't talk too much about that in this tutorial, but it's an interesting property that comes up in sensing, which is that if I take the same sensor under the same conditions and take a measurement, does it give the same result or not? Right? So is it repeatable? It's something they care a lot about in real sensors. So those are some characteristics. I think I'm done with physical sensors, and now I want to go to a virtual world and start explaining things. So I want to make models of the physical state space. I'm going to start distinguishing between physical sensors, like these pictures I showed you, and virtual sensors, where it's just a mathematical model of the information that we get from a sensing system. And I want you to keep in mind that a virtual sensor that I define could have many different physical sensor implementations. Right? So I'm not, if I do invent some kind of virtual sensor model that I'm going to give you, I will do it because I believe there's at least one or more possible implementations of that in the physical world that produce that kind of information. Otherwise, I don't want to just invent weird virtual sensors, let's say, that have no physical correspondence. I'd also like to identify, this will be really interesting, is that which virtual sensor among the space of possible virtual sensors, this is something we'll get to, will lead to better filters and better planning algorithms, and will cause you to live, let's say, in a better information space. Some smaller information space, one you can compute more easily over, and that sort of thing. Right. So one of the key ideas here, I'm going to try to understand how two spaces are related. And I'll give more and more definitions and a lot of examples. And the second part of today, in the last second hour of today, I'll give even more. Kind of go through all of these. This will be like kind of like we're shopping at the mall here. I'm going to give you all the different kinds of virtual sensors. So we have to pass through all of them and look at the different types and compare them and such. And that's why there's many different types of sensors here if you look at what's coming up. And then I'll talk about the important structures that we build on top of them to compare them and such. And you will see some models in there that remind you a lot of pursuit evasion and invisibility and these kinds of things. So I hope it'll be interesting for you. Number one, the two spaces we relate, one is going to be called the physical state space. And actually by that I mean a mathematical model of the physical state space. So the physical state, in some ways, I would call a cartoon-like description, a perfect kind of description of what the world looks like, the external world looks like to the sensor. Right? So we're going to take measurements from the physical world, but I want to make a mathematical description of that physical world. It doesn't mean I'm going to measure everything in it, but I just need a description of it. And then we have an observation space, which is the set of possible sensor observations. What measurements can the sensor take? And so sensors, the most basic sensors will do, most of the ones we'll look at, just do an instantaneous conversion. They convert the physical state into a sensor observation, or sensor reading, or sensor measurement. Right? So that's what happens. Poof, the sensor tells us something about the physical world, some kind of information. So that's how it's going to look. So let me start off with a very simple example to think a little bit about. So suppose I have a robot, the yellow disc there, and it's pointing in some direction. It has like a laser scanner, laser pointer if you want, and it can measure distance. So maybe, imagine I'm the robot, so it's pointing in this direction, and it receives an observation. It says, the wall is 3 meters away. That's what it gets. Well, what is it that you know? That's a very interesting kind of question. What uncertainty is there, right? So suppose you know the wall is 3 meters away in the direction that you're facing. Well, what is there to characterize? In some sense, what you should think about it, and we'll get through a lot of examples of this, but what possible external physical worlds are consistent with that measurement? Right? One of the things that will become important is, did I tell you what the room looks like or not, right? Because if I tell you exactly the shape of this room, imagine this room's a perfect rectangle, let's say, with no furniture or people, then if I tell you that it's 3 meters away, where could you be? And what orientation could you be in, right? So there's very important things you could start to deduce from that. If I don't tell you what room you're in, then you're in a much larger space because there's possible rooms you might consider. That's the kind of stuff we have to think about. So here's a common structure that's going to come up. Have you heard of localization and mapping in robotics? So localization is the problem of figuring out where the robot is at. And mapping is the problem of determining where the walls are at, let's say, or where all the furniture is at. Everything that you have to interact with, it's not what your actual coordinates are. So one of them is telling what the world looks like around you, the environment looks like, and one of them is telling where you are inside of it. So if we had a localization only problem up at the top there, then if we're only interested in that problem, then we have to consider the set of possible configurations, right? Where might the robot be? If we have a mapping only problem, we're looking at very carefully the set of possible environments. When we look at both, this is actually often called SLAM, right? The simultaneous localization and mapping. What we really have is a set of configuration and environment pairs. Right? There's possible environments and then possible places where you might be in that environment. So that's going to cause a common kind of structure in some of the things I talk about. And I'll just give a kind of an abstract way of looking at it here. Just say, look, there could be any set of sets, Z, let's say, right? So a collection of sets or a set of sets, and then so that's fancy Z, and then every regular Z is what we call a map, let's say. So fancy Z is like a collection of maps, if you want, and then we have to also make sure we're consistent in that every little Z inside of there is just your place in the map, or configuration of the map. So if I have an unknown configuration and map, then I'm going to have a state space that looks something like this. It's all pairs, little z and big Z, such that little z is in big Z. In other words, your place is somewhere on the map, and your map is somewhere in your atlas of maps, if you like, right? Your collection of maps. So that's a common structure you're going to see over and over again. I think it's very nice to think about this, that this thing will happen again and again. So I'm going to give some examples of that. Right, let's think about the state space for a planar mobile robot. Very much like the kind you might imagine for visibility-based pursuit of agent and things like that. We're just moving around in the plane. And let's first keep it very simple. So let's say that we have no obstacles. So the robot could be in any position in R2, let's say. So we have QX and QY for the positions. The robot could be in any orientation, let's say, Q theta. So 0 to 2 pi, right? So it could be in any orientation going around. And then the state space is just the set of all positions and orientations. So how might this look? Well, we could imagine then that the state space is just a subset of R3, right? Because we have 3 coordinates, an x, a y, and a theta. We have to be a little bit careful. So I'm told you have some topology background, right? So maybe it's the case that here it is the case that 0 and 2 pi represent the same orientation, correct? So you can look at it as a subset of R3, but you have to be careful that there's some location, there's some repeat, right? So really, you should only restrict the subset to be between 0 and 2 pi, and you should not have copies of both, and you should know that when you increase up to 2 pi, you immediately jump to 0, right? So it wraps around, it's circular in that direction. So because of that, some people write this Cartesian product of R2 cross S1. I probably should have, I can say equals here, yeah. I do say equals, that's right, because I picked R2. So R2 cross S1, where S1 is considered the circle of all rotations. Is that fine? Does the set of all rotations in the plane seem like a circle to you, right? I can specify the angle, and I go all the way around, and I paint a circle, right? This is the way people write it in mathematics for this space. This is SE2, the special Euclidean group. That's the set of all two-dimensional rigid body transformations. It's all things that is the it's called the 3x3 homogeneous transformation matrices, if you want. It's matrices that allow translation and rotation together in one operation. So these are 3 different ways to look at the same thing, and these are the basics. We're very familiar with these because of configuration spaces in robotics, right? So and I think you've had some introduction to that, right, in the previous days. All right. So any questions? People getting sleepy? It's a little warm, right? Maybe kind of.
actually just relax a little bit on the observation state and the physical state.
Yeah.
Many relation, or you consider one-to-many relation?
We're gonna get there fairly soon, but this idea here is going to be many to one. Then we're gonna later consider some models where we have disturbance, and then it could be many to many. Then, like we say, okay, even though the physical state is this, the observation could be any of these because of disturbance. But I really want to emphasize a lot in this tutorial the many to one part. The fact that there's a whole bunch of states that all map to the same thing, that causes uncertainty. And then I want to say, if you understand your task well, it's okay to leave that uncertain. Just like in pursuit evasion, it's okay to not know the position of the evader. You can leave it uncertain to make a good strategy. I want to show many, many more examples of that and try to encourage people to go off in different directions maybe, and hopefully it'll lead to a lot of interesting open problems for people to study. That's my hope. But no, it's a very good question, and that's exactly right. I'm not many to one is the way it will look. Well, let's look at the state space if I give you a map, let's say. So let's say E is a subset. E is supposed to be the white subset here of R2. I don't know if that's green or what, but the greenish there, greenish blue is the obstacles. I move my robot around, and I'm drawing my robot as a disk here, but let's just pretend it's a point. Okay, make it really small. I don't want to deal with configuration space obstacle nonsense here. It's too complicated for this. But I don't want to illustrate that part. I don't care too much. But so imagine the robot's really small here relative to the size of the room. Well, if that's the case, then here, the way the state space looks is that I could be in any position inside of E, correct? E is the white part there. And then I still have S1, right? Because I can be in any orientation. So the state space for this is E cross S1. Now I say, I'm not going to tell you E. Instead, E is like one map. Instead of the map, I'm going to give you a collection of maps. It's like a book of maps, right? It may also be like, I could give you the architectural plan of this building. Or I could give you a book of architectural plans and say, yeah, I don't remember which one this building is, but here's the book of them. And your robot's going to be in one of those. Right? So if I give you something like that, then it could be like this. I say there's a set of possible maps. Maybe there's 5 of them, let's say, right? And then if that's the case, then I get this kind of structure immediately. And for that structure, remember that that's the same as this thing I did with the Z's a bit ago. See this? Remember this is what I did with the Z's? I made this slide. Same thing here now, but it's going to have E's in it. And it will be, the state space is a set of all configurations and environments for which the position part of your configuration is in the environment, E sub I, and that E sub I is in your collection of maps. So that's really the space you're in when someone gives you a collection of maps. If I give you 5 maps, that's how it looks. If I give you K maps, that's how it looks. Now, I think it's more fun to give you an uncountably infinite number of maps. Right? So then your map book would be quite large then, right? So that's fine. But hey, it's math. You can define whatever you want. So, and these large state spaces will be quite useful. So for example, let's see. For example, maybe I say that your collection of maps or environments, just look at I give a lot of examples there, but let's look at the first one. It could be all connected, bounded polygonal subsets that have no interior holes. In other words, as computational geometers all know, it could be the set of all simple polygons. Right? So that could be your collection of maps. I just say the robot is placed in a simple polygon. Good luck. Right? Your map book is pretty large there, right? So it could be simple polygon. Let me just kind of draw one. I should make a joke right now. Let me do that. This is how a computational geometer might present a simple polygon, right? And this is how a control theorist might present a simple polygon. I don't know if you get the humor or not, but basically control theorists always like convexity, and they always want the thing to be as simple as possible because they don't want convexity and complications to occur. So the simple polygon means it really is, simple. Right? To a computational geometer, simple means, well, we better think about the worst case and how bad the polygon can get. So that's a simple polygon, right? So it's kind of a funny counterintuitive thing, right? Now maybe I can expand this previous case here to include holes, right? So maybe number 2 there, bullet number 2, says, well, it could be the space of all polygons like this, but I also have some interior holes that are also polygonal. Oh, they don't have to be convex either, I guess. I'm not being a good imaginative computational geometer in this case. So all kinds of crazy holes and such, right? So that's another collection. Maybe it's all subsets of R2 that have a finite number of points removed. That's another kind of model, right? Let me make that one over here.